This is section 3.10, Linear Approximations and Differentials. In this section, we will be approximating a function using the linearization equation that is constructed by the tangent line equation at the point A. Since, as we have seen earlier, that a curve lies very close to its tangent line near the point of tangency. And here we will consider that A is the point of tangency. Let's have a look at an example. So we have to find the linearization of the function f of x, which is the square root of x plus 3 at a equals to 1. And we will use it to approximate the numbers square root of 3.98 and 4.05, and then we should tell whether they are overestimates or underestimates. To start by the first idea, which is finding the linearization, we know that L of x is going to be f at a plus f prime at a multiplied by x minus a. Basically, this represents the tangent line equation, so we have done something like this before. Now, to be able to find the linearization, we'll find first the values of f of a and f prime of a. Now, f at a is going to be f at 1, which is the square root of 1 plus 3, which is 2. F prime at a, we will find it, but first we should get f prime at x, which is 1 over 2 multiplied by x plus 3 to the power of negative 1 over 2, using the chain rule. Now, f prime at a is equal to f prime at 1, so it will be 1 over 2 multiplied by 1 plus 3 power negative 1 over 2, which will make 1 over 4. Now, to just substitute in the linearization formula, we will use the values we just found here. So f of a is going to be 2 plus f prime at a, we found it, which is 1 over 4 multiplied by x minus a, which is 1. Now if we distribute 1 over 4, we multiply it by x and then by negative 1, we get 2 plus 1 over 4x minus 1 over 4. Now 2 minus 1 over 4, if we unify the denominator, we get 1 over 4x plus 7 over 4. So this means that L of x is the linearization is 1 over 4x plus 7 over 4. So our function can be approximated using this expression 1 over 4x plus 7 over 4. Now we have to approximate the numbers 3.98 and 4.05. If we compare these numbers to the function that we do have, our function is x plus 3, and the value that we should get is 3.98, which means that we can write this in this way, 3 plus 0.98. So our x is going to be 0.98, and 4.05 can be written as 3 plus 1.05. 1.05 here represents the x. So if we want to approximate these functions, we'll be approximating f at 0.98 first. So f at 0.98 is going to be somehow equal to 0.98 over 4 plus 7 over 4. And this will give us 1.995. And if we try to approximate f at 1.05, we have to just substitute using the linearization expression we got, plus 7 over 4, and this should give us 2.0125. Now, to investigate whether it was an overestimate or underestimate, we use our function, which is f of x equal to x plus 3, and we use the values here. So here we have to substitute by 0.98 first using the function. So this will be 0.98 plus 3. Now square root of 3.98, if we use the calculator, we will get 1.99499 and so on. If we try to find f at 1.05, then it's going to be the square root of 3 plus 1.05, which is 2.0124618. So basically for this one, we can see that what we got, the approximation was 1.9995 and this one was 1.994. So we can see that this is an overestimate. because the approximation we got was more than the actual function at 0.98. And at this point, also it's an overestimate. So for both values, it was an overestimate because f at 1.05, it was approximated by 2.0125, and the actual one was 2.012468. Let's have a look at the differentials concept of this section. So basically here we can define dy to be f prime of x multiplied by d of x. And this is coming from the fact that dy over dx can be represented by f prime of x. So if we multiply both sides by d of x, what we get is this differential. Now here we have, in this example, to compare the values of delta y and dy if y is the given polynomial function, and as x changes from 2 to 2.05 and from 2 to 2.01. To start with a, we should first get dy, which is f prime at x multiplied by dx. So basically we know that the x we have is going to be 2, and d of x is the change that happens from 2 up to 2.05, so it means 2.05 minus 2, which is 0.05. Now to find the derivative of the function, the given function, it will be 3x squared plus 2x minus 2. Now f prime at the x, which is 2, it's going to be 3 multiplied by 2 squared plus 2 multiplied by 2 minus 2. This will give us 2, and 3 times 4 is going to be 12. 12 plus 2 is going to be 14. Now to put things of dy is going to be 14 times the dx, which is 0.05, and this will give us 0.7. Now to find delta y, we have to get f at the ending point, which is 2.05, minus f at the starting point. So this means that we should find f at these two values. F at 2.05 is going to be, so we had x cubed, so this will become 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. We just substituted using 2.05. Now if we use the calculator to calculate this, we will get 9.717625. And now if we want to substitute using 2, we will get 2 cubed plus 2 squared minus 2 times 2 plus 1. So this is 0, and we have here 9, because this is 8 plus 1. Now delta y is going to be 9.717625 minus 9. And the result is going to be 0.717625. As we have found earlier, we got that the differential dy is 0.7. So if we want to compare between them, we can see that basically delta y is greater than dy, and the difference is between very few places. Now let's do part B, where we have the x is moving from 2 up to 2.01. Now our x is going to be 2 as before, but the dx is going to be 0.01, which is 2.01 minus 2. Now to start with the differential, we have to get f prime at x multiplied by d of x. As we have found earlier that f prime at 2 is going to be 14, but our dx now is different, which is 0.01. Now dy is going to be 14 times 0.01, and this will give us 0.14. Now delta y is going to be f at 2.01 minus f at 2. To find the value of f at 2.01, we just have to substitute with the function that we do have. It's going to be 2.01 cubed plus 2.01 squared minus 2 times 2.01 plus 1. And this will give us 9.140701. And f at 2, we found it before, we got 9. Now delta y is going to be 9.140701 minus 9, and this will be 0.140701. In this case, we can see also that delta y was greater than dy, because dy was 0.14 and delta y was 0.140701, and the change is slightly different. It's not a huge difference. Let's have a look at this example where we have the radius of a sphere. It was measured and found to be 21 centimeter with the possible error in measurement of at most 0.05 centimeter. Now they want the maximum error in using this value of the radius to compute the volume of the sphere. To start by, we know that the volume of the sphere is going to be 4/3 pi r cubed. Now if the error in the measured value of r is denoted by dr, which is the delta r, then the corresponding error in the calculated value of f is going to be the differential of v. Now if we want to differentiate v, this is the differential v, so this will become dv, and if we try to differentiate this, 3 will be cancelled with the denominator. We'll get 4 pi r squared multiplied by dr. Now we know something here, that r is 21 centimeter and the dr, which is the error, is 0.05 centimeter. Now if we try to compute this using the values that we do have, dv is going to be 4 pi r, which is 21 squared, and the dr is 0.05. If we try to compute this, we will get approximately 277. Now the maximum error in the calculated volume is about 277 centimeter cubed. So this is using the differential. We could know the maximum error using the radius that might have an error in measurement of at most 0.05 centimeter.